In this video, I aim to perform a coordinate transformation on the line element for 3D curved space. So to begin, we will write out the line element in 3D in terms of the functions s kappa of chi squared d omega squared. So this equation represents the distance between points in curved space, which is a function of the radial distance chi and the angular dependence d omega. The coordinate transformation we wish to perform is to swap r and the functions s kappa chi. In this case, we know that the functions s kappa of chi are given by three individual functions: r sine chi over r, chi, and r sine chi over r, for kappa equals 1, kappa equals 0, and kappa equals -1 respectively, which correspond to positive, flat, and negative curvature respectively, which can be thought of as spherical, flat, and hyperbolic. Here, big R represents the radius of curvature of the space. Pretty clearly, we can see that we can swap this s kappa squared term here for r squared, which will be the easy part. Next, we need to determine what d chi squared is going to become. To do that, we will take the derivative of the functions s kappa. I like to think of the functions s kappa as representing the changes that we have to make to flat space to account for curved space. So what we'll do is we will find dr by d kappa, which will be equal to ds kappa of chi by d kappa, for which we can get three different results. We get cos chi over r, 1, and cosh chi over r. Again, for kappa equals to 1, 0, and -1 respectively. The derivative here should be rather clear, but you can see that by applying the chain rule, the big R in front of the sine and shine cancel with the 1 over R within the brackets of the trigonometric and hyperbolic functions. We can rearrange this for d chi, which will be equal to dr over the ds kappa of chi by d chi, and therefore d chi squared will be equal to dr squared by the square of the derivative of these s functions with respect to kappa. So this r squared term here is fab. That's what we want in our coordinate transformation of the line element, but we now wish to find a more suitable form of the denominator which has no chi dependence. So taking the derivative of the s functions and writing them out explicitly again, we can notice that we can use trigonometric and hyperbolic identities to write these in terms of the original functions s kappa. In this case, especially when we take the square, in fact, let's just write out the square. We can see that these squares are easily obtained. We can use hyperbolic and trigonometric identities to write these in terms of the original functions s kappa. In this case, the kappa equals to 1 term can be written as 1 minus sine squared chi over r. The 1 can just be written as 1 or 1 minus 0. This will make much more sense than a few lines down. And the bottom one here can be written as 1 plus sine squared kappa over r. You can see that these come from the trigonometric identities sine squared theta plus cos squared theta equals to 1, and this one here comes from cos squared theta minus sine squared theta equals 1. We now know that these functions themselves are the s kappa functions scaled by 1 over r squared. So if we took the square of the s kappa functions, we would have r squared sine squared chi over r. We'd have chi squared and r squared sine squared chi over r. Therefore, we can write these in terms of 1 minus s kappa of chi divided by r squared. This one here is just, again, 1 minus 0. And 1 plus s kappa chi divided by r squared. These should be squares as well. We now note that we performed the coordinate transformation s kappa chi equals to r, so we can substitute the r in here. But this won't hold for all cases. We would still have to have a kappa dependence. But we note that the only difference between these three equations, or especially the top two, the top and bottom one, is the sign. So we can actually write 1 minus kappa s kappa chi squared over r squared, which is now true for all kappa, including the middle one, because in the case where kappa equals to 0, this entire term equals 0. So we can now say, and by substituting in s kappa equals to r, we get 1 minus kappa r over r squared. We can then substitute this into the equation for the line element that we had earlier, noting briefly that our d chi squared term is dr squared over 1 minus kappa r over r squared, meaning that our line element in 3D, ds3 squared, is equal to dr squared over 1 minus kappa r over r squared plus r squared d omega squared. And this is our final answer for the coordinate transformed version of the line element for a generally curved surface, either spherically, flat, or hyperbolically, with constant radius of curvature r, big R.